physics class. I'm serious. Today we're doing physics. Too bad. You're now signed up for physics class. 27. No, 30 overall. Okay, 30. Yep. We're talking about physics. Okay? And forces. So today we're going to talk about forces on objects and use trig to solve the problems. Such as, here's a box. And there are forces of 5 pounds and 16 pounds on this box. So we got 5 pounds going this way and 16 pounds going this way. How do I know they're going this way? Because it says they act at an angle of 90 degrees. So one guy is pulling with 5 pounds of force going to the right. Another guy is pulling 16 pounds going this way. Where will the box go? Well, it won't go straight up because it's being pulled this way too. So it's kind of going to go up at an angle, right? So we use what are called, Mr. Hodgins' favorite, head to tail vectors. We're going to put a vector right here, which is going to be the same as a 16-pound force. And then we're going to draw what's called the resultant vector here. Okay, let me even get really fancy with this. And highlight it. That's going to be our resultant vector. Okay? So, as you can see, we make a right triangle here. Okay? So the magnitude of the resulting force is the what theorem? Pythagorean theorem, right? Or, as we learned the other day, the square root of 5 squared plus 16 squared. Okay? Well, we know 5 squared is 25, and 16 squared is like 256. So it's the square root of 208. 281? Right? What's the square root of 281 rounded to the nearest tenth? 16.8. So it's being pulled at a force of 16.8 pounds in that direction. What direction is that direction? Well, we make our little symbol down here, theta. That's the angle that we need to find. Okay? So, opposite over adjacent is what trig function? Tangent. So we take the inverse tangent of the opposite side over the adjacent side. Again, something we did the other day. Well, a week ago. Well, a week and a half ago. Because we had pi day in there. So what's the inverse tangent of 16 over 5? How many degrees is that? The inverse tangent of 16 over 5. 72.6. So, what's going to happen to this box? It's going to go more this way than this way at an angle of 72.6 degrees. And it's being pulled at a force of 16.8 pounds in this direction. Okay? So this is what you do for part of physics class, is you look at forces and figure out what's going where. Okay? So, now, my most favoriteest trig problem of all time. Okay? 2 prospectors are pulling ropes attached around the neck of a donkey that does not want to move. That donkey is being an angle side-side. because it doesn't want to move. Hey, I got to throw in my comedy wherever I can. Okay? One prospector pulls with a force of 60. The other one pulls with a force of 70. The angle between the ropes is 20 degrees, as shown in the figure. How much force must the donkey use to stay put? Because with forces, for every force this direction, there is an equal and opposite force in the other direction. Or there's an equal force in the opposite direction. Newton's law of whatever, forces, something like that. So, whatever the prospectors are pulling in this direction, the donkey's pulling back in this direction. Okay? So what happens is we just make a head to tail vectors here, which makes, what kind of a shape is this? And I know this is not perfect, but what kind of a shape does this kind of look like? A parallelogram, did I hear? Yeah, it's a parallelogram. And what do we know about opposite sides of a parallelogram? They're equal to each other. So this is 70 and this is 60. Now, in a parallelogram, let me redraw a parallelogram down here. If this is 20 degrees, okay, what does this angle up here have to be a parallelogram? Because consecutive angles of a parallelogram are supplementary. Did I hear a 160? I did, and that is correct. That's 160 degrees. So to figure out this force right here, we have the side of the triangle, a side of a triangle, and the angle in between. I have side, angle, side. What do we use to figure out a side, angle, side triangle if I want the opposite side? Law of, not law of sines, law of cosines. Exactly. We're going to use the law of cosines. So x squared equals 60 squared plus 70 squared minus 2 times 60 times 70 cosine of 160 degrees. Then we grab our handy dandy calculator and we're going to just type that on in. So we take 60 squared plus 70 squared minus 2 times 60 times 70 cosine of 160 degrees. That's an awful big force. Oh, very good, people. I have to take a square root of that because that's what x squared is. So if I go second square root of the answer, I get 129.2. And that's how much force they are pulling the donkey. And that's how much force the donkey is pulling back away from them. Now, these prospectors are doing a pretty dang good job. They kind of sort of know their physics. What would make them better at doing their job, better at pulling the donkey? If they were pulling in what type of a line? A straight line. If they're both holding on to the same rope, or if one rope was shorter than the other and they were in a straight line, they would be combining their forces together. Because they split apart at a 20-degree angle, they're wasting a little bit of their force. Do you know how much force they're wasting in this situation? Only 0.8 pounds. So they're not really wasting much force because they're only separated by 20 degrees. Because if they were together, he would be pulling at 60, he'd be pulling at 70, they'd add up to 130. Well, this is 129.2, so they're wasting a little bit of energy, but not too much. But that is my most favoritist problem of trigonometry of all time, the donkey problem. All right. Because it's fun, because I get to say angle side side without saying the word that I'm not supposed to say. All right. Now, this is not a realistic situation, this last one. But let's say this was a realistic situation. A block of ice weighing 80 pounds is sitting on an incline of 38 degrees. We all know it would be sliding right down the incline. So there must be a lot of friction keeping that ice where it's at. Now, the force of gravity pulls this straight down. That's gravity, the force of gravity. What keeps it on the ramp is the force of friction. Okay? So gravity pulls it down this way. The angle of the ramp pulls it down that way. What we need to figure out is what this force is right here that's pulling it that way. Okay? Because we know the force straight down is 80 pounds. Okay? The force of friction is holding it up. Okay? We want to know this force over here. Now, we know this angle is 38 pounds. What's the smallest angle on this triangle? The bottom angle or the top angle? The bottom angle. So it must also be 38 degrees because we're working with right angles here. So if this is a right angle with this, then this 38-degree angle is transferred to here. Okay? So this is a right triangle here. This is my hypotenuse. The force of gravity is my hypotenuse. How much something weighs is the force down of gravity. We want to figure out the force going down this way because that's the equal and opposite is the force of friction back this way. So if we have the opposite side, we have the hypotenuse. What trig function is opposite of hypotenuse? Sine. So the sine of my 38-degree angle equals x over 80. So if we multiply both sides by 80, x equals 80 times the sine of 38. Somebody take 80 times the sine of 38 on your calculator. $49.3. So the force of friction is 49.3 pounds, keeping the block of ice on the ramp. Okay? And there are answers, and somebody screwed up on this. Must have typed something wrong on their calculator. Because this is supposed to be 128. Did I screw that up? I bet I did. 60. Okay. Let me go to my mode. Oh, I'm in radian mode. I need to be in degree mode. Make sure your calculators are in degree mode for this problem. So if I go back up here and hit enter and hit enter, I get a different number and then take the square root of that answer. I get 128. So yeah, they're wasting about 2 pounds of force by being separated by 20 degrees. I figured something was not